Hey guys, welcome back to Computational Biology with Python. In this lecture, we're going to be doing thresholding and image processing for hopefully phenomics and learning about how to find phenotypes. So let's go ahead and jump right in. Okay, first things first, we're going to go to this website. You could just go to this website, this GitHub website, and go to chapter 3, and then you want to download the rainbow JPG, and you want to download the crossword JPG. And then we'll come back to Praxis. And so I'm going to upload rainbow and upload crossword. Okay, so let's do import cv2, import matplotlib.pyplot as plt, and then we need to do our matplotlib inline, and now we can do image equals cv2.nread, and we'll start with rainbow.jpg in there .jpg. Okay, and then we can do plot imshow image. We should have our nice rainbow plot. Beautiful. So let's do some thresholding. So what if we want to cancel out background colors or things like that? So if we do image cv2.nread rainbow.jpg, and then we do 0, and then we do plot imshow image cmap equals gray, put quotations around that, you can see that we have sort of reduced the color of the image, but what we want to do is we want to take this and we want to threshold this image. So there are different thresholding techniques and values. We're not going to get too much in the weeds about how the math behind it, because it's can be a bit much for our purposes, but I just want to show you some of the things that you can do. So ret1 thresh1 equals cv2.threshold image, and then 127 255 cv2.thresh binary. So now if we do ret1, you can see we have a value of 127. So that is our so there's 255 pixels in these images, and so 127 is near half the pixels, right? It's half as we can get without doing a decimal. So that's our cutoff value. So everything above the 127 is going to be changed one color, and everything below is going to be changed another color. So let's do plot imshow thresh1 cmap equals gray. So you can see we have a bit of a gradient, or a threshold, where we said anything that's this lighter color is going to turn white, and everything that's darker is going to turn black. So if you think about this from my problem that I started with at the very beginning of the section. So you can see in these images, we have a very dark background for my plants, and we have a very white root tip and stem of these plants. So a technique to measure these could be built around thresholding. It's kind of difficult because we have some difficulties at the time when I started to do this, because you have this like whitewash from the lights, so it had a hard time thresholding. It just kind of made this all one big blob. But also at the time, this camera had been on the space station since like the mid 2000s, and it had started to get bombarded with cosmic radiation. And so what has happened is we get these like this pixelation that has occurred in our pictures, where these pixels went bad because exposure of radiation. And so it was a little bit outside of my expertise in getting it to work. But theoretically, if I were to do this, and maybe now the tools, like after I already did like I said, 6 months of measuring, and this is published already. But I think that would be my first step, right? Is to do a threshold where I could just have black and white and then measure lines as opposed to dealing with all these colors. So that's kind of like what we have here, right? So we can also inverse the limits. So we can do something like this: image 2 equals cv2 mread rainbow.jpg, and then we're going to say 0, then rep1 thresh1 equals cv2.threshold image 2 127 255 cv2.thresh trunk, and then plot imshow thresh 1 cmap equals gray. Let's see if there's no typos in that. Nope. Imshow is not defined. Plot.imshow. And there shouldn't be that. Okay. So you can see we changed our, we've inversed the limits. So if we compare this, we had a threshold binary where we said we want 2 different colors. Here we've changed it to this thresh trunk. So let's see what thresh trunk does. Thresh trunk. So adaptive threshold, right? Applies an adaptive threshold to an array. It transfers it into a binary image according to this formula. So it's adaptive. It depends on nearest neighbors and things of that nature. So you can see we have a different outcome based on that technique. We can also do something like image 3 equals cv2.2.imread rainbow.jpg, and then 0 ret1 thresh1 equals cv2.threshold image 3, and then we do 127, which was the half that we said, out of 255, cv2 dot thresh 2 0, and then plots dot imshow thresh 1 cmap equals gray. So as you can see here, we have, it almost looks kind of 3D, right? Okay, now let's do this on a quote-unquote real-world application, that crossword page that we had. So we're going to do def show pic image fig image, this should be, there we go. Fig equals plot figure, fig size equals 1515. I'm going to say AX equals fig add subplot 111. And then ax imshow image cmap equals gray. Okay, so we're making this function to display our images. So we're going to show our pick. Oh, we need to first, so before this, let's add a block, because I skipped a point. You can, you can drag it right here. There we go. Image r equals cv2.imread. We gotta load our crossword. Crossword.jpg, and then we're gonna say 0. Now we're gonna say plot.imshow image r cmap equals gray. Okay, now, so we have our crossword picture. Now we run this, and now we run show our image. So you can see we have our crossword, newspaper crossword. You probably don't even, a lot of you don't even remember these, because no one gets newspapers anymore. Okay, so let's, now we can kind of cut out, so what this function does is cuts out a lot of these other aspects that we have to, or code that we have to do. We're at th1 equals cv2.threshold image r 127 255 cv2.thresh binary, and then show pick th1. So that's our function, right? Show pick. So you can see here, if we're we have to take a step back. So what's the point? So what we want to do is keep all the black text in the gray text, and turn it into like a white. So just like a kind of like a Word document, right? Or a PDF where it's just white on, or black on white, and not this gray stuff that we have going on like a newspaper. So here, not so good. Different techniques will give you different results. So we have a lot of noise with this binary one. So let's try changing the threshold. Ret th1 equals cv2.threshold image r 200 instead of what do we have, 127? Is that what we were doing before? Yep, 200 and 255 cv2 dot thresh binary, and then show pick th1. So there's a bit of a art to choosing the binary or the numbers that will give you your best results. You know, you have to kind of look at it case by case in this example. But we can do some different techniques to see if we can get better results. So let's try th2 equals cv2 adaptive, excuse me, man, adaptive threshold image r 255 cv2 dot adaptive thresh mean c cv2 dot thresh binary, and then we need to add 11.8. All right, so now let's do show pick show pick th. Oh wait, show pick th2 for threshold 2. So this adaptive threshold, you put the source, you put the max value, the adaptive method, which was our adaptive thresh mean, and then you do the threshold type. So we did binary, and then you do the block size and the C, which we're not going to get into too much. You can play with those values if you want to see what they do different. The block size essentially is a pixel size of the neighborhood that is used to calculate a threshold for a particular pixel. So it looks at the image and says, okay, what color are the neighbors? And if this one's really significantly different than the neighbors, then we'll make them two different colors, right? Yeah, we won't get into the Gaussian mean. But as you can see, we have a good rendition here compared to the first two, except it didn't fill the boxes in the crosswords, right? So we want it to look like this, where the boxes are all black. But this method just outlines the boxes, and it doesn't give us that fill-in that we wanted. So we can blend this to do different thresholds. Add weighted src1 equals ph1 alpha equals 0.6. And then we're going to do source 2 equals ph2 beta equals 0.4, gamma equals 0, show pick blended. So this is just like we did before. We're layering two on top of each other, right? So we're layering src1 and src2. So this was th1 and th2. So this was th2, and we layered that underneath th1, which is this one, and then gave it a. That's why like the boxes are gray in the middle, because it's layering white on black, right? So you get gray. All right, let's do one more example, then we'll call it quits. So let's look at Gaussian. So th3 equals cv2.adaptive threshold image r, 255 is our max, cv2.adaptive thresh mean c, cv2.thresh binary, and then we do the 11 for the nearest neighbors, and then the 8, and then let's do blended equals cv2 dot add weighted src1 equals th1 alpha equals 0.6, so we're going to put them on top of each other again. src2 equals th3 beta equals 0.4, and then 0, or you can put gamma equals 0, and then show pick blended. I guess I do have to put gamma equals 0 in this case, maybe because I'm doing two of them. Okay, I'm not sure what I did. I just removed the spaces and we're good. Maybe there's a typo, I don't know. But as you can see from this last one, we get probably the best version. I guess it's kind of debatable between the two. But essentially we've removed the background, right? We have some pixelation, and you could further process it or play with the values to try to get it perfect. But yeah, so that's background removal, right? So if you were doing something, so one of the issues that we had, so if I look at this sunflower heliotropism video, this video might not be, so, oh, of course we get an ad, and I can't mute it. So one of the issues that we had was, where's a good picture? Was that our images it was like this, right? So we had an image where we were trying to track a green object, but they were grown in a field where there were other plants in the background. So it was hard to pull out the plant from its background. I guess this would be kind of a good image, right? So like pulling this part out from all the stuff in the background was very difficult. So thresholding, if you can tune it in right, or here's another good one. So, you know, because of the focus, we can see this, but if you look at just the colors, what's differentiating this sunflower in the foreground or this sunflower head in the foreground versus the background? And so thresholding comes in when you're looking to phenotype in this regard. So say I wanted to automate this program to measure the diameter of seed heads like this. And how do I get that to happen? If I could probably threshold this kind of lighter color green from the darker color greens around the edge of the flower, or try to threshold this whole head from the background. But it was something that we had issues with. And so these techniques, like I said at the time, I was not a programmer. So it was, we were just trying to use programs that were already built and published. And so being able to optimize this yourself is really important and can be useful for doing these type of thresholding processes for automation. So that's it. That's one of the, we use these examples like some of these built-in examples with like crossword puzzles and things like that, but there are real applications, so I don't want that to get lost in the ether, that there is actually things that are these are very applicable to biology. So thanks for watching. I hope you enjoyed the video. If you're watching on YouTube, please hit like, please hit subscribe, and we'll continue on our computer vision journey in the next video.